All right, so we have 3/4 divided by 1/2. So the first thing I do in a problem like this is I just restate it as a question, so then I can figure out how to answer the question. So how many times does 1/2 go into 3/4? Okay. So then once I have the question, I usually just redraw that division box that we use a lot for long division. So I'll put that up here. I've got 1/2 goes into 3/4. And so now I just need a picture of 1/2 and a picture of 3/4 to kind of show that. So first thing I'll do is I'll just do it as cakes. And so this can be my 1/2. And I want that to go into 3/4. And colors, let they go. There we go. So here's my 1/2. Oops. Here's my 1/2. And then 3/4. Okay, that's my best coloring between the lines today. So the next problem I have is they're not cut the same way, so I got to make the pieces like so I can do accounting. So I can just cut that 1/2 and 1/2, and now I have quarters. Right? So I have 2 things over here, and I have 3 things over there. So I'm looking for groups of 2. Are there any groups of 2 in where I'm looking? Yeah, for sure there's 1 group of 2 there. So there's going to be a 1 in my answer. And the question is, how does that compare to the group I'm looking for? Right? It's 1/2 of what I was looking for. Yeah, so it looks like there's 1.5 groups of 1/2 in 3/4. That's what that tells me right there. Right? Because I'm looking for this in that. Right? So another way to think about this is you have the, let's see, say this is have, and this is need over there. So I need groups of 1/2. And I'm looking to see how many of them there are. Another cool thing about the answer, check this out. Up here, didn't I write have divided by need? Right, so another way to write that is just have over need, right? Because doesn't that mean divide? How many pieces do I have?
3.
Okay. How many pieces do I need? 2. So the answer must be 3/2. Is that the same thing as 1.5? Mm-hmm. So that's kind of another way to think about it. Do we do it with the hexagons? Just for fun? Okay. So, and most of the time I think the hexagons are an optional thing. The nice thing about them is they are fun to manipulate in your hands. And squares like that are easier to draw on paper, but harder to get a set of toys that does the same thing. So let's do it again. I need some dot paper. Let's see, I got some somewhere. There it is. Look up a little. Oh, wrong button. There we go, screenshot. And if on the test, either you have to or you decide to use hexagons, I'll bring these with me, whip them out, and do it. Okay, that's totally different than drawing it for your mind. So I think it's worth thinking about that. Okay, so to show 3/4, what would have to be a whole here? It have to be 2 hexagons, right? So we want to be clear up front what a whole is. Tracking well. Okay, so this is 1 whole. And then I want to show, let's see. I need 3/4 divided by 1/2. How many 1/2 in 3/4? So I'm taking 1/2 into 3/4. So then I want to redraw it with that in mind. So I'll redraw my half here. And then that's going into my 3/4. Different. Okay, so somehow we have to decide how to cut them, and I think the easiest thing to do here is just take the half and cut it in half. And then it's not a bad idea to make a note looking for groups of 2. So then over here, we can start highlighting. There's one group of 2 right there, so there's definitely going to be a 1 in my answer. And then it's then figuring out what to do with what's left over. And I have 1 out of the 2 things I'm looking for. So it's still 1.5 that way. How's it going? You guys look like not at all excited about this. We do another one, no more warm up, and move on to ratios.
That would be good.
Okay. So again, you could have done it with circles, squares. The hexagons are mostly optional. There was one problem on that take-home test where I asked you to use the hexagon stuff, but I think, wasn't there? Yeah, but it's usually an option in my opinion. Okay, so how about do you want it about the same difficulty? Sound good?
Yeah.
Okay. I was thinking hard. A sec. All right, let's try this one. 1.5 divided by 2/3. So write your question, restate it with the goes into symbol, and then see if you can draw a sketch of how many 2/3 are inside a half.
Should be the
This is what I do. Not 2.5.
Yeah, that's what I was.
That is very
boring. Do this couple weeks. And try to do something.
Where's your phone?
And just in the hole.
Oh.
I don't know.
I think. Oh, okay, because in the halves it'll be split into twos rather than fours. Yes. I don't know. I'm confused.
Division's hard. It's okay to be confused. So I'm gonna do mine with cakes, and if I'm gonna draw it with a different set of pictures, I can after. So I'm trying to figure out how many times 2/3 goes into a half. And so I decided to draw square cakes, and here's my picture of 2/3, and there's my picture of 1 1/2. Okay. Once I draw that, I think, oh, I could call this 3 halves instead. That might help. So next thing I realize is, well, it's hard to find the blue things and the red things because they're different shapes. So what should I do next? Cut them like each other. So I need to go and say, okay, let's cut these guys in half and cut these guys in thirds. Okay, now what should I look for next? Yeah, so this side over here, now that I have like-shaped pieces, is groups of 4. So I'm just going to make a little note that I'm looking for groups of 4 over here. And then I just start finding them. So here's one group of 4, and then 1, 2, 3, 4. Here's another group of 4. So for sure I have 2 groups of 4. And then the question is, what's that leftover guy? 1 out of, what am I looking for?
4.
I'm looking for groups of 4. So that's 1 out of the 4 things I'm looking for. Yeah, so the answer should be 2 and a 4. 4, sorry. Now I'm looking for groups of 4. I found one whole group of 4. I found another whole group of 4. And then I just got 1 out of the 4 I was hoping to find. So essentially, once I cut things up like this, I've turned my denominator up here into a thing called 4. What did I turn my numerator fraction into? How many red shapes do I have now altogether?
9.
6, 7, 8, 9. And so I've turned this problem into how many groups of 4 are in 9 is the equivalent problem here. So next I'm just going to go over a few different algorithms for how to get the job done without drawing pictures. Does anybody want to see a different set of pictures?
We see it in the hexagon.
In the hexagons? Yeah. So with the hexagons, we could get by with 1 hexagon for this because the hexagon can be easily split into thirds or halves. Yeah, that would work. Or we could use 2, whatever your preference is. What do you want to do?
I did 2.
Okay, so I'll do it that way. So I'm trying to figure out 2/3 goes into 1 1/2 how many times. So then using 2 hexagons, so I draw that. Ooh, that's faster. I guess I should have dot paper. Try and get it out. Oh man. I'm gonna do this. Focusing really hard. Okay, all right.
Sorry.
I think I'm good from here. You're fine. Okay, so then thirds, let's see, that was that
The chevron.
chevron type shape. Okay, so there's my chevrons, and I want 2 of them. Okay, so there's my 2/3. And that needs to try and go into
Oh.
1.5. So, go ahead. There's 1. I think it's copy that. That would be a great idea, wouldn't it? Once I have a digital whiteboard. Okay. So here's my 1.5. And we come across the same problem we had before, is they're not cut like the other. So we have to go through and start cutting them up. So these guys need to be cut into half. Oops, color, red. So cut in half, cut in half. So now that's nice, I have the rhombus type shape, and then I go split these guys up into rhombi. And ideally, I would much rather be playing with the toys in front of me to do this than drawing it. Okay, so now I got it. So what am I looking for again?
Groups of 4.
And I'm still looking for groups of 4, because I gotta have a common piece to be able to look for groups of stuff. So I'm still looking for groups of 4, and then we just start finding them. So let's say there's one group, and then here's a second group, and then we still have that one piece left out of the 4 we're searching for. Yeah. So if I have dot paper and maybe the toys nearby, I'm gonna whip out the hexagons. If I don't, I'm probably gonna draw cakes or pies, whichever is feels good at that point. All right, so next, algorithms for division. So I'm going to present an algorithm that comes from these pictures, which isn't commonly taught, but it's kind of cute. So we were just trying to take 1.5 and divide by 2/3. And I'm going to rewrite that by calling it 3/2, because 1.5 is 3/2 divided by 2/3. And I mentioned before, when you have to do a calculation, it's almost always way easier to do it using improper fractions than mixed numbers. So just pretty much that's the strategy. Okay. If the books you're using at school teach otherwise, teach this instead and don't worry about it too much. Okay, so next thing is, I had to cut each like the other, didn't I? Which means I had to find a common denominator. So what's an obvious denominator here? 6. So then we convert these guys. So we say, all right, you're going to be multiplied by 2 top and bottom. You're going to be multiplied by 3 top and bottom. So now I have 9/6 divided by 4/6. Okay, so we just find a common denominator. And here's the best part about the next thing. Once you find a common denominator, forget about it. There's your answer. 9/4 is the answer. Make it into a mixed number if you want. Okay. So 4 goes into 9 twice, with 1 left over. So you could say the answer is 9/4. That is a perfectly great answer. Is it reduced? Does 4 and 9 have any common factors? Nope, it's totally reduced. However, if we need to communicate this in some way, 2/4 is a better answer for communication. So the algorithm goes like this. Step 1, find a common denominator. Step 2, just divide the numerators. You want to make a side note? Forget about the denominators at this point. Don't need them anymore. Once we have a common description, division really is just looking for groups of stuff. We know the groups we're looking for. We don't care that there's 6 anymore. All we need to know is how many 4s are in 9. So this is an algorithm. It's a process that works for any pair of fractions that you try to divide and come up with an answer. Interesting thing happens when we do this. It's the denominators that we were focusing on here. So that 3 right there, and this 2 down there. And ultimately, didn't we end up ditching the denominators completely? So this 3, where did it go? It went up to the numerator over there. Where'd this 2 go before I ditched it? I put it up there. So there's kind of a cross-multiply thing going on here. So the better way to look at an arrow algorithm for this is in the following way. Important note is you got to have improper fractions, not mixed numbers. So improper or proper, but not mixed numbers. So we'll take the one we're looking at. We have 3 halves divided by 2/3. The focus here is the denominator because that's what we're looking for groups of. And so you take the numerator and you cross multiply it down. You take the denominator and cross multiply it up. 2 times 2 is 4, 3 times 3 is 9, 9/4 has to be the answer. So this is called the arrow algorithm for dividing fractions. And that's more often taught than it used to be. You'll see that come up in books these days. And then there's the traditional algorithm that most of you should remember. Traditional. 3 halves divided by 2/3. Okay, what do you guys normally do to carry out this division besides whipping out a calculator?
Switch it.
Yeah, you switch which fraction?
The second.
The second one, yeah. So we would rewrite this as 3 halves times 3 halves. We flip it. Multiplication is easy. You just multiply numerators, multiply denominators, and there's our, again, our 9/4. So the idea here is that division is the same thing as multiplying by the reciprocal. So the algorithm is, another name for it is just multiply by the reciprocal. Instead of dividing by 2/3, we multiply by 3 halves, and out pops a nice answer. So you guys are different than elementary school kids because you got to have a better grasp on it than they do. It's unlikely you're going to draw a lot of pictures of fractions like we did because that's slightly higher level thinking than just carrying out the algorithm. And in general, algorithms tend to be easier to teach, but we want to teach more than just do what I tell you, memorize these steps. So you're not going to show a lot of that, but you will with the addition. You'll see that in the books. You'll see the demonstration of a fraction, subtraction with pictures. You'll see the demonstration of areas as multiplication, but you won't see as many pictures going with the division because it's just a way harder thing to wrap kids' minds around. So just a note on that. Let's see. I think that's about it for division. Any questions? We got 3 different algorithms we can apply with division. Lots of fun pictures. Right. Speaking of pictures, is anyone taking a look at the practice exam I posted? Oh, good, we got way more nods this time. Cool, there's answers there too for some of the problems. So if you haven't taken a look, take a look.
Is that going to be Wednesday?
Yes, Wednesday. Yeah. All right, next bit of fun and games, we're gonna take a look at ratio and proportion. So the idea of ratio came up already when we were in section 1 in terms of what is a fraction. Can somebody give me an example of a fraction as a ratio? Yeah, ratio of like boys to girls. Two boys for every 3 girls in a group. Can you think of any other common ratios? I'm gonna make pizza when I get home, and when I make pizza dough, common ratio of flour to water is 3 to 1. Every 3 cups of flour, I need a cup of water to get the dough sticky enough, but not too sticky so it makes a nice pie. Another one I use a lot. To get to school, I have to drive through residential neighborhoods. So a common one that's in my head is 20. 20 what, do you think? Yeah, miles per hour. Okay, so every 20 miles, 1 hour goes by. Speed limit's usually 25, but I usually go for 20 for 2 reasons. One, there's lots of weird streets in Pendleton, and I've been hit before. And 2, there's lots of kids around, and getting hit at 20 miles per hour versus 25 is a substantial difference. And so, rates, there's lots of rates we use. I like the bicycle. If I'm in good shape and the ride's not too long, I can hold up 15 miles per hour for a while. So there's lots of rates. If you're driving on the highway, anybody commute like between Pendleton and Hermiston or Pendleton and Walla Walla or Portland, are there speeds you gauge when you're on the highway? Like what's the optimal speed that you won't get pulled over at driving on Interstate 4?
75.
You usually get 75 after that. Probably going to get pulled over, right? So we use rates all the time in a lot of different ways. So think some more about some rates that you might come across. And rate is sometimes thought of as different from a ratio. Usually think about rate, we think about like the time it takes for something to happen, but not all ratios involve time. Good Monday? Okay, that's right, I'll help you out with some more. So in geometry is full of cool ratios. There's something called the golden ratio. So golden ratio comes from what's called the golden rectangle. And a golden rectangle is one where that if you were to cut a square, to make believe that red part's a perfect square, the remaining rectangle has the same shape as the original. If a rectangle has that property, it's a golden rectangle. If it's a golden rectangle and you take the long side and divide by the short side, you get what's called the golden ratio. Okay. And it's approximately 1.6-ish. And it's been found in architecture dating back thousands of years. So people have had an artistic view of this idea for a long time, which is kind of neat. And it pops up other bizarre places too. The golden ratio pops up in the way sunflower seeds are distributed in a sunflower. It has something to do with beehives, but I can't remember what. And there's a whole bunch of other places that it pops up in nature. So it's kind of a cool number. That bring to mind any other magical ratios from geometry? Fondness upon your high school geometry. I know we already talked about that. I see frowns. Yeah. Exactly, pi. Good job. Pi, what does pi have to do with? Circles, right? So if you know the center of the circle and there's a line passing through the center, what do we call that line? The diameter. And if you take any circle and you can perfectly measure its diameter and you can measure its circumference, pi is the ratio of the circumference to the diameter on any circle. And that's something humans have known about for thousands of years. We know a lot more decimal places than we used to. At first, pi was about 3, and it was 3 and a little bit. The popular one that Egyptians came up with was like 1000 BC. It was about 3 1/7. And I think that came up around the same time in China and some other places too. The weird thing about pi is although it comes from a ratio, it cannot be written exactly as the ratio of whole numbers. That means pi can never be a true fraction. It's this other weird number. In the decimal system, it comes out as this weird string of digits that never repeats a pattern, ever. It's kind of bizarre. So just a quick note on the difference between numbers that do have a pattern and numbers that don't. Whip out a calculator if you got one. Let's see if I can get my Google calculator to work today. I bet it's going to fail. How about 22 divided by 7? So 22 over 7, that's the improper version of 3 1/7, which was a number we thought pi was about for thousands of years. 3.142857. What do you notice about the next few digits? 1428. Ah, darn, there's a 6. But what do you think happened there, really? That 6 was probably supposed to be a 5 followed by a 7, so the computer rounded that from a 5 to a 6. And if I had a calculator that showed more digits, I would see that. That sevenths have a repeating pattern of 142857, 142857, 142857. We'll look at that a little more in the next chapter. Common one, 4 9ths. 0.4444444444. Another interesting one, let's suppose I had 13 over 99. 0.131313131313. Okay. So pretty much any pattern you pick, any fraction you pick, excuse me, well, one of two things will happen. Either it'll stop, like 1/4 is 0.25, or it will repeat the same pattern over and over and over again. A fixed number of digits repeat over and over again. There's a reason for that we'll study in the next chapter. But it turns out there's a ton of numbers that do not have this property. They don't end and they don't repeat a pattern. Those types of numbers are called irrational numbers, and pi is an irrational number. So this idea that it cannot be written as the ratio of two whole numbers, that's the idea of a fraction, a rational number. Pi then must be an irrational number. even though it comes from one of the most famous ratios in human history. So it turns out if the circumference happens to be a whole number, the diameter can't. If the diameter happens to be a whole number, the circumference can't. If one of them happens to be a regular fraction, the other one can't, because of this idea of irrationality. And that's a whole other branch of math we're not going to quite get into, but it's just a really weird idea. Okay, further, think about triangles for a minute. So if I take, for example, a triangle and make believe all the sides are the same length there, and then I cut it in half, I get this new shaped triangle that looks like this roughly. And one cool thing about it is it has a right angle. Other cool thing about it is that a triangle, if you look at the interior angles, they always add up to 180 if you add all three of them up. So if I take 180 and divide it by 3, what do I get? 60. I get 60. So each of these angles must be 60. So this one here is 60 degrees. This one was cut in half, so that one's going to be 30. So this is a popular triangle called a 30, 60, 90 triangle. You may have come across it in some geometry class. Cool thing about that is there's lots of 30, 60, 90 triangles out there. This triangle right here could have 60 degrees there and 30 degrees there. But they're different shapes. They're different sizes, but they're the same shape. These are what are called similar figures. Similar figures have same shape but maybe a different size. They could have the same shape but a different orientation. Like here, I have the short side in line with the ground. What if I rotate it so the short side was in line with the wall or the ceiling? So similar figures have the same shape. Cool thing about that idea, so I would say this figure here has a long side, it has a short side, and it has a medium side. If you were to take, maybe I should use capital letters. Let's make that a capital M, make it fancier, and a capital S. And then it's capital L. If you take a ratio here, like the long side, and you divide by the short side on the big figure, if this truly is the same shape, meaning it has the same angles in the same order, then let's call this little l and little s. Then the ratios of this one are going to have to match. Whatever the long side is divided by the short side has got to be the same. So a common example of something like that we can use, take a big blue tree, and a person. And the sun is shining somewhere up in the sky. And what does the sun tend to do on the ground? It makes shadows. So the sun's going to cause a shadow for each of these. And so let's say the shadow is coming down at that angle. So the angle that the sun is hitting the ground on for the tree is going to be the exact same angle that is hitting the ground for the person there. If you imagine that there's an upright from the center of the tree to where that angle starts up there, there's the same thing for this person. So when the sun makes shadows in a given area, then it's going to cause triangles that are similar. Now, would you agree it's going to be kind of hard to measure the top of a tree? So we can, and surveyors use similar tricks, not with the sun, but they use spotting devices and measure angles. So we could measure the length of the shadow here. So let's say we measure the length of that shadow, and it comes out to be 20 feet. And we measure the length of the person's shadow, and let's say it comes out to be 5 feet. And we know the person is, say, 6 feet tall. Then we can set up a ratio. The ratio I would set up here is I'm missing the height of the tree, so I would choose to put height in the numerator. And then I have the shadow length, which I can just call length. And I think it's a good practice. Anytime you set up proportions, which are two equal fractions, you write in words what you're doing first, then you do it for each object. So here for the tree, I do not know the height, but I do know the shadow length. And if they're indeed proportional, same shape, then the person has to have the same thing. Its height divided by its shadow length have to match in ratio. So as long as I establish what kinds of things go in the numerator and what kinds of things go in the denominator, I can now come up with the height of the tree if my other measurements are okay. So, come up with the height of the tree.
24.
24? Yeah. So we'll look at that in a couple of different ways. So I've got question mark over 20 is equal to 6 over 5. So the classic way to solve a proportion is to cross multiply and then divide. So then I'm going to get 5 question marks equals 6 times 20. And then we divide. And so question mark has to be whatever 60 divided by 5 is. Oh wait, I can't multiply. It's 6 times 20. 120. And then we'll find 5 goes in 120 24 times. Double check. Do we believe that 24 over 20 is the same as 6 over 5? That seem reasonable? So when I realized that I had made a mistake multiplying, I was coming up with the answer of 60 divided by 5, and I was picturing that 12 up here. And I was realizing this couldn't be smaller than the denominator. There wasn't a reasonable answer, so I had to have made a mistake. So it's always a good idea to check. So tell me 2 different ways I can check to see that this is the correct answer, that 24 I put there.
Yeah, common denominator,
Could find a common denominator. And what would you go for a denominator?
20.
20, so we would multiply top and bottom by 4. 4 times 6 is 24, so that would check out. Okay, so that's one way to check it. Can someone come up with a different way to check?
Reduce 24 times over 20.
Yeah, 6 over 5 doesn't reduce, but 24 and 20 have a common factor of 4. 4 goes into 24 6 times, 4 goes into 25 times, and so we get 24. 20 is reduced to 6/5. Okay, 2 ways. Can we come up with a third way to check it?
Cross multiply again.
Cross multiply again, yeah. Check to see if 5 times 24 matches 20 times 6. That would work. We're on a roll here. Can we come up with another way to check it? Do we have a calculator nearby? Yeah, on your calculator, you can just type what's 6 divided by 5, get a number. What's 24 divided by 20, get a number, hope they match, because we're claiming that they're equal. So there's lots of ways we can play around with checking a proportion. Cross multiplying is one way, which is a good one because that's how we got an answer in the first place. All right, let's see. Take a couple more examples of this. So just some formalities. So a ratio is just the quotient of two numbers. And it can be any two numbers. When we talk about earlier in the chapter in section 1, we talked about rational numbers. Anybody remember the definition of what it meant to be a rational number? Rational number was the quotient of two whole numbers. So like 1 over 2, or 3 over 1, or 22 over 7. When I talk about a ratio, it can be the quotient of any kinds of numbers. They don't have to be whole numbers. So it could be something like 2/3 over 1/2. That's a ratio. We could simplify it into a rational number by cleaning that division up, but it's still a ratio. Another common one, if you've ever had trigonometry in your past, pi divided by 2 is the number that comes up all the time. Pi is not a whole number. So this number right here, pi over 2, can never be written as a rational number, but it's definitely a ratio because it's two numbers divided. So ratio just means take two numbers and divide them. They don't have to be whole numbers. Rational numbers, a special kind of number, it's numbers that can always be written as the division of two whole numbers, just slightly different. The ratio, two numbers divided, usually those numbers have meanings. Another important idea here, the idea of a proportion. Proportion is two equal ratios. The example that we just saw, 24/20ths is the same thing as 6/5. So that's the simple idea of a proportion. And what we do is we harness the power of this equal to solve problems that we couldn't solve otherwise. Like back in that other problem, we used this powerful idea to find that missing number 24 that we couldn't directly measure. All right, so back to proportions, and then we'll play around with a couple other ideas related to it. So proportion is two equal fractions, and let's suppose I'm going to call the numerator y and the denominator x. And maybe it's two similar triangles, maybe it's related to a speed, maybe it's related to a recipe. There's lots of places ratios come up. But the bottom line is, if things are proportional, they have a common ratio. So we're just going to say y over x is always equal to some other number r. So I'm using r here just to refer to the common ratio. And we're just going to play with algebra for a moment. So y over x, I could rewrite this to get rid of a denominator. How do I clear a denominator in an equation? Anybody recall from their algebra days?
Multiply it.
Yeah, multiply it. So I could multiply both sides by x, and I get a new way to express this relationship, that y is equal to r times x. And a sibling to this equation, remember y equals mx plus b from algebra? What does that kind of equation mean? You can recall.
The slope is rise over run.
Slope, that's n, that's our rise over run, right? So this is our slope. Slope is rise over run, yeah, and what else?
V is the y-intercept.
V is the y-intercept or vertical intercept. And the only difference between the blue equation and the black one is the black one has an R instead of an M, big deal, it's just some number. But the B is missing. So if it's missing, what must it be? What can you add on when nothing happens? Yeah, it's 0. So this is the equation of a line here. In general, and it turns out a proportion is a line with 0, 0 as the y-intercept. So I'll just illustrate that in a picture. So think back to graphing, and here's our x-axis and here's our y-axis. And let's suppose this is my line right there. And this is y equals, I'm calling it r times x. R for ratio. And notice I made it come from this point right here, which is the point 0, 0. Which, does anybody remember the name of that point in the grid here?
The origin?
The origin, yeah, that's called the origin. So a proportion is always the same thing as a line that passes through the origin, that has a y-intercept of 0. And if you look at it here, Tiffany said that slope was rise over run. So if I wanted to get from the blue point to the red point there, I would have to go up a certain amount, that was called my rise. And I have to go right a certain amount, that would be called my run. And the slope is our rise over our run. And that's just some point. That point has an x value and it has a y value, right? So in particular, if I'm calling that point xy, I had to go up by y, and I had to run by x. So my rise over run is just y over x. So the slope, and that's earlier, right? Isn't that how I started, that common ratio is y over x in a proportion? So I'll use this as an example in a minute. So I'm just connecting the idea of slope is that common ratio. I'll relate this back to that shadow problem. So here's our x and here's our y. And I'm going to say the y is going to be the heights we're looking at in the shadow problem, and the x are going to be the lengths that we have with the shadows. And the thing we knew for sure is we could measure the height of the person and we could measure the person's shadow. We couldn't measure the height of the tree. And what we found is that if we went up 6, that's the height of the person, and we went right 5, the length of the person's shadow, that gives us a significant piece of information, which here I'm just showing as a point. So any line I draw, and keep this in mind, if there's no shadow, there's no height. Okay, so 0, 0 is an important point, and then from there I have to head up through that point. So this would be the line related to the shadow problem. What can you tell me about the slope of the line here? What's the rise to get from here to there?
6 even.
Rise is 6 and run 5. Yeah, so it's 6/5. And looking back at the shadow problem, here we go. 6/5 was an important number, right? When we made that problem, it was the ratio of the things I knew, the person. So if I keep moving out 5, let's see if I can do that. Here's another 5. So 5, 10, 15, 20. And I trace that up to my line and over to the y-axis. Can we figure out what number that has to be right there? So that's going to give us, in this case, instead of having a change of 5, we have a change in the bottom of 20, right? That's the way we're running. We just need to figure out what's the corresponding rise. And we already figured that out. What's the corresponding rise going to be? 24. So to be on this line, you always have to change by a ratio of 6 to 5. If you don't do that, you'll fall off the line. Does that make sense? What if I tried to go up 10 over 10? Will I be on this line still? Now, if I do that, if I go over 10 here and then I go up 10, I'm going to fall short of where I need to be. The only way to stay on this line is to be consistent with the 6 over 5 idea. So what's 6 over 5 as a decimal? Anybody?
1.2.
1.2, okay. So 6 over 5 is equal to 1.2. And I could write that as a fraction by calling it 1.2 over 1. So what that tells me is if I rose just by 1.2, I would only have to do a run of 1 to stay on the line. What if I were to rise 24? How far would I have to run? Oops. Number. I would have to do what? I would have to go 20 in order to stay on the line. So what's my point here? You, as individuals, have a lot of math. The cool thing that we've just connected is the idea of a line with a y-intercept of 0 is the same thing as a proportion. Where two things that you can measure, every time you divide them, you get the same answer. Okay, with that in mind, are people essentially the same shape? In that, like with a triangle, I can see a triangle and say, yeah, that's another triangle. I can see a right triangle, another right triangle, I can agree they're both right triangles, right? If we see a bear walking down the road, we're not going to confuse that with a person, right? And you've seen some really crazy movie with aliens and other scary things that clearly aren't people because their limbs are too long and their heads are too big or whatever. So people have a definite look to them. I asked you guys to make some measurements. Did anybody happen to make those measurements? Okay, so if you got those measurements, get them out. If you didn't, I have some stuff to measure with. You guys need some measuring devices there? Yeah, so if you didn't make measurements, team up here. Did you make your measurements?
No.
Oh, man, okay, team up with them and get some measurements. If you made your measurements, get them out. I'm gonna make a spreadsheet here of our measurements. So we're gonna play around with people proportions.
Did you want to
What's that?
Did you want them in centimeters?
If they're not in centimeters, we'll convert them.